Warangal. He is working as a professor in NITI Warangal. Another one is 30 years experience industry person. He is taking dimensions in data analysis. Okay. But yesterday I make some inconvenient to somebody's crash WhatsApp group. Okay, now I created the new group also. Don't post anything, sir, because we are all one team only. If anything required means you can personally you can inform me. Definitely we will help you. At the same time, Google Form once you link you are shared to you, try to fill at early because I have to give the answer to the AC. At the same time, even you can fill the 1 day later, the time will be appear. That you can't hide. That you know very well. Google link will be kept as a active. But thing is, what time you can fill the Google link? That also recorded in the
Okay. Is it visible, sir?
yes, sir. Visible, sir. Visible. Visible.
Okay. Thank you. So, today topic is actually 3D printing, additive manufacturing. But I think already one session completed, 1 or 2 sessions on the 3D printing. So I'm not going to discuss about the 3D printing or additive manufacturing process. My most of the content is on the precision finishing of the uh, 3D metal printed components. So, but I'll just give you an introduction. I think you already know this, but anyway. So, this 3D printing or additive manufacturing is a method of creating a three-dimensional objects. So normally we are using a CAD model and we are giving input file to the system and connected to the printer. And so that we are building a part layer by layer. So that is what if you see, we start a 3D model like this, and then maybe we can give this one to the system, and then we build the component layer by layer like this. Uh, excuse me, someone is using the screen.
Sir, whiteboards. Whiteboards, sir. No, I have stopped the access.
Okay, thank you. So
Sir, share your screen, sir.
sir, I am sharing my screen. The same thing. I will show you another figure. So this is electromagnet, and this is the magnetic abrasive brush, which is shown in the previous figure also. Same. So if you enlarge this one, the brush is like this. So that means this is the abrasive particle. Actually, the workpiece surface is like this.
Okay, so we have peaks. So we know the workpiece surface is like this. So then abrasive particle is striking here and it is striking to the surface. These peaks are removed in the form of a chip, and slowly this surface may become like this and we get a smooth surface like this. So it is nothing but like grinding process or lapping process or honing process. We are removing the peaks and we are making the surface less roughness and also finished. So this is the principle of magnetic abrasive finishing. And this is the actual photograph from the setup. So here you see, this is the workpiece. You can see this white one. This is the workpiece, and this is the electromagnet. This is the magnet, and here this is the brush. This is the brush. Once it is rotating, the brush is moving on the surface, so we can able to remove the material in the very small particle form. So this is magneto-abrasive finishing. So normally these are the parameters which we can able to change. That is, one is machine settings, that is rotational speed, etc. And then working gap. So this is called as working gap. This is called as a working gap or maybe standoff distance. And then we can able to change the input current or voltage, or maybe we can change the finishing time, and we can change the speed of electromagnetic. Speed of electromagnetic is nothing but rotation of electromagnet. So these are the parameters normally we change from the machine. So machine settings are this one, which are going to change the working gap or input or output current, no, input current or voltage, and finishing time and speed of the electromagnet. Similarly, we can able to change from the abrasive media also, right? So in the abrasive media, what we can able to change is we can change the type of abrasive particle. Either you can use SiC or Al2O3, and also the particle size, that is nothing but mesh size of the abrasive particle, and also percentage of abrasives. That means how much amount of iron powder we have to mix and how much amount of abrasive particles we have to mix, and then abrasive type or abrasive type, size, and percentage. So these are the three parameters we can able to change in the abrasive media. And then the magnetic media, that is either we can use ferromagnetic type or any other electromagnetic type, etc. So this is also we can change. So by changing these parameters, maybe we can able to change the output parameters, or we can able to get different output performances like material removal rate or surface finish or residual stresses, etc. So this is again the in detailed photograph showing. So this is a slip ring called a slip ring, and this is the winding, and this is the electromagnet. So this part is inside the machine. This is nothing but a milling machine. So we used a normal milling machine which is available in the machine shop. So we replaced this milling cutter with this one, and then this is the final setup. So you can see separately, this is the electromagnetic tool. We can call it as the total combination is called it as electromagnetic tool, and this is the fixing of the tool into the milling machine. And this is what when the machine is running, this part is the flexible magnetic abrasive brush. So you can see this is the workpiece we are fixing into the vise, right? This is the vise, we can fix it, and we move the work table either in this direction or in this direction, so that to cover the total surface of the workpiece, and to move this flexible magnetic abrasive brush on the total surface. So this is what the setup. Uh, so then, okay. So then, once after doing this process, the surface finish or surface roughness or microstructure of the components are like this. You can see this is the component before the process, and this is the component after the process. Of course, this is not additively manufactured component. This is normal component. I will show you additively manufactured component later. So this is the normal component after grinding. So this is the microstructure of this component from the SEM, and this is after the MAF process. So you can see a lot of difference is there. So all these scratches and burrs are removed in this process. But still here also a small indentation will be there. That is called as abrasive indentation marks. So and this is what the initial roughness value, that is 1.3 micrometers, and the final roughness now is 0.325 micrometers. So that is RA value actually what we measured. So, what is happening here? That is what the abrasive particles removes material through a combination of two things, that is mechanical abrasion and magnetic forces. Why? Because the magnetic forces are used to rotate the brush, and while the brush is rotating, the abrasive particles are striking to the surface or rubbing on the surface and removing the asperities from the peaks. And then here the control movement of the workpiece and distribution of the abrasive particles, which results in a very precise and uniform surface finish, because here the material removal rate is very less, right? But the finish is very good. The dimensional accuracy is good and the finish is also good. So we can get the repeated impacts on the surface, okay, and then shearing off takes place from the peaks, and then finally in this particular trial experiment we got 1.3 micrometers to 0.325 micrometers. So then the surface asperities or grinding grooves are removed effectively by this process. Okay, so this is what uh, magneto-abrasive finishing and the surface finish what we observed and the microstructure what we observed. So here these process applications normally we can use in the aerospace industry, that is for finishing of turbine blades or engine components or any other structures, and also we use for medical devices to get the smooth surfaces on the surgical implants or medical devices to improve the biocompatibility, right? Because the bio implant should be very smooth. And also we use for finishing of the gears, shafts and engine components in the automotive industry. And also we use the same process maybe in the tool and die making industry, that is finishing of the molds or dies or tools. And also we use in the precision machinery. So wherever we want very good finish on the machine, there we can use this process. So these are all the applications of the MEF process. And advantage is here the precision. That is, we get highly precise and uniform surface finish, and this is very versatile. That is, it is applicable to different range of materials for both metals and ceramics. And also here the tool wear is not there because very minimum, because we can use abrasive particles and iron powder for a longer time, because this is not exactly a tool. We are just using the magnetic field and we are binding the iron particles and abrasive particles together in the form of a circular brush, and then we are using that. So the tool wear is very very less. Here actually tool wear means that is losing the sharpness of the abrasive particles. So like in the grinding process. So this is very very slow. After a long time only we have to replace this one, and then it is very effective on the complex geometries, like we use a brush, like sometimes we use a brush to polish our shoes, or we use a brush to clean our teeth. Also we use brush like that. It is flexible and it goes into intricate shapes, and it reaches the hard to reach areas which are not possible with grinding operation. But there are certain limitations in this process. That is, normally a non-ferrous materials or unresponsive magnetic field materials, it is difficult to machine, uh, right? So that is actually, if the workpiece is ferrous material, then maybe the magnetic field also affecting that material. That's why only we use which are not affected by the magnetic field. That is only we can able to finish by this process. That is normally non-ferrous materials or any other metals which are unresponsive to the magnetic fields. And also it requires some special setup, like we need to arrange a this flexible magnetic abrasive brush, then only we can able to use it. So now the same process, a little advancement. So here in the previous process, the workpiece is having only while the brush is rotating like this, the workpiece is stationary. Once this area is covered, then I can move the workpiece to the next place, or in this direction, or in this direction, or maybe in this direction. That is either X or Y direction. But along with this rotation of the brush, if you get movement on the other direction, that is, if you see in the top view, actually the workpiece is like this. So the brush is rotating like this at certain position if you are not moving the workpiece. Instead of this movement, if you get a random movement like this, if you get a random movement like this, then the material removal may be more uniform, or maybe it is giving more influence. So with that idea, the next level of the process is developed, that is called as ultrasonic assisted magnetic abrasive finishing. That means for the same magnetic abrasive finishing, we are adding a vibration. That means while this is rotating, we move the workpiece in this direction with the help of giving vibration to this workpiece. That means we give vibration to the workpiece here. So with the help of the transducer and ultrasonic power supply and generator. So this is the generator, and this is the transducer, and this is the horn. So this generator creates the vibrations, and this vibration is transferred to the transducer. You know, all of you know the functionality of transducer. The same thing, it stabilizes the vibration and it enhances the vibrations. And this horn also useful to enhance the amplitude of this vibration, so that the amplitude or the vibration is given to the workpiece in a particular direction. So if the workpiece is moving like this, the brush is rotating. So then like that, we move the brush throughout the area of this one, like this total area we cover. Okay. So while giving this vibration to the workpiece. So this spring is used because this vibration is pushing the workpiece in this direction. At the same time, when the transducer is moving in this direction, the spring is used to push the workpiece to the original position. Like that, like in the dial gauge, when the force is acting on the plunger moves upwards. If you remove the force, the plunger moves downwards. Why? Because already internal the spring is there, which is always trying to push the plunger downwards. Similarly here, the spring is trying to push the workpiece always in this direction, and this transducer is pushing the workpiece in this direction, but at a particular interval with certain amplitude. So that's why here we get the vibration or a simple harmonic motion like this. So this is nothing but combining the ultrasonic vibrations, magnetic fields, and abrasives to enhance the precision and surface finish on the various materials. So this integration of ultrasonic energy optimizes the material removal rates, and also it is more beneficial for intricate components and complex geometries. Because of these movements, we are able to cut the material in different shapes. So here the principle is integration of this MAF, whatever we discussed already, with the ultrasonic machining. By integrating these two, the ultrasonic vibrations we are superimposing into the magnetic field, and we are removing the material removal in a better manner. So again, this one is applications are aerospace industry and automobile industry, and working on metals as metals or ceramics or composites for super finishing process. So this is a little bit improvement for the magneto abrasive finishing process. So here also same thing. Some of the parameters are from the previous one only. Only one parameter here changing is amplitude of vibration. Okay, so all parameters are same in previous process and this process. Okay, right? The machining setup, that is rotational speed, working gap, that is speed of electromagnetic means rotational speed, finishing time, and current or voltage. All this is machine setups. So along with this here, we can able to change the amplitude of vibration also. Normally, it is difficult to change the frequency because this generator contains a fixed frequency. So this is the original setup. So if you observe the previous one, the workpiece previous setup, the workpiece is fixed in a vise, but now this is fixed in a jig. Okay, jig, a fixer. This is a fixer. So I think all of you know the difference between jig or a fixer. Okay, right. So the fixture is helping to get the movement. So workpiece is here, and this one is a fixture, and this fixture we are keeping on the dynamometer to measure the forces, etc. So here we have this is the horn, and this is the transducer, and this is the ultrasonic generator, so which is connected to the wire and then to the generator. So here this one is giving vibration in this direction, right? And I will show you how this workpiece is coming back when this is moving. So this is the same machine and the total setup is same. Only we are keeping the workpiece in a jig with the setup of giving the ultrasonic vibration. So actually this one is now the same setup, either MAF setup or UMF setup, we can use for the 3D printed components. So why it is useful is actually finishing of additive manufacturing components is very important because the additive manufacturing components are having very complex shapes, and we need to reduce the surface roughness, and also we need to provide a uh, very accurate dimensions, and we need to provide consistent and precise material removal rate. So because already this is additively manufactured component, if you remove the material in a very accurate manner and very little material removal rate, then you get the better finish. So normally, it go for internal structures or challenging cavities or maybe irregular surfaces, or this making UAMF very flexible and control material removal, which is very crucial for achieving the uniform surface finish. So these additive manufacturing components required all these things. That is why this process is more suitable for this one. Then here the combination of ultrasonic vibrations and magnetic force not only enhances the precision but also improves the surface integrity. This is what very important here. Already I told you in the starting itself, surface integrity means we need to understand the surface damage like micro cracks or surface asperities or roughness, etc., as well as residual stresses. So then this UMF efficiency to produce the smoother surface finish make it very valuable technique for enhancing the overall quality and dimensional accuracy of the additively manufactured components. So I am justifying why this UAMF is more suitable for 3D printed components. Okay, so these are the reasons where the applications of this UAMF is more suitable to 3D printing components. Of course, these are suitable for other components also, but 3D printed components are more required by this one. So this is one case study. So normally this is uh, AL-Si12Mg material, then printed by SLM process. So this is the SLM machine, right? So these are the machine specifications and these are the parameters. So we fabricated these samples, these workpieces, so different workpieces, uh, and we kept all the parameters in the 3D printing process constant, because here we need to understand, we want to see what is the influence of the finishing process on the first post processing. That is why we are not changing any parameters in the 3D printing or dimensions, etc. All the samples are manufactured by the same machine, same dimensions, same parameters. And then after printing these components, some of the components we took as it is, that is non-heat treated condition, and some of the components we are taken in the heat treated component condition. Why? Because already we discussed in the starting itself, the heat treatment is also one of the post processing technique which is useful to relieve the stresses or to get the porosity, better porosity, etc., right, or density, etc. So then this is the setup. Already I told you. Here in this view, you can able to see these are the springs, right? So always these springs pushing the fixer in this direction, and this horn is pushing the uh, this one, that is fixer in this direction. That is the movement is like this. Okay, and actually this is all the fixer, this one is a fixer. Okay, the component is actually below this one because of the cost effectiveness, I mean to reduce the cost, we printed a very small samples. Okay, right? So then uh, the sample is in below this brush. So this is the brush formed by MAF process, and the vibration is given by ultrasonic assisted setup. So by combining these two processes, we are achieving the UAMF process. Okay, and these are the standard values we followed to uh, fabricate this setup, and these are the values we followed just to see the how the finishing is taking place. Later on, we changed parameters also, right? So this is UAMF of the additively manufactured components. So now I will show you different samples. First, we took non-heat treated sample. So this is the one that is as it is 3D printed component, and this is 3D printed component, but grinding. So this is a heat treat finishing. F means non-heat treated finishing. This is non-heat treated as it is component. So this is a non-heat treated, but we performed grinding operation on this. Okay. Sorry. This is finished by UAMF, and this is the grinding operation, right? And this is initially performed grinding and then performed finishing. So we took 4 samples. This is the as it is sample. This is directly finished sample by UMF, and this is finished sample by grinding process, and this is the sample finished by grinding plus finishing. So if you observe this one, actually this is giving the better result. Even from the microstructure you can able to see. So the direct finishing on this one, that is the second component, in a fine surface finish at some areas, but there are abrasive indentations. So this area may be fine, but here or here there are differences. So which is not required for us, or that is unwanted thing. So initially if you grind and then finishing, then we are getting the better quality in this one. So then the same thing repeated on the heat treated sample. So this is the heat treated sample as it is, which is from the 3D printing process, and then this is heat treated and finishing sample by UAMF process, and this is heat treated and grinding sample, and this is heat treated, grinding and finishing by UAMF process. So if you see, this is having even better surface than the previous sample. That means because of the heat treatment also the surface is slightly improving, and if you perform the grinding and finishing operation on the heat treated sample, then because of the readjustment of this porosity adjuster, etc., then we are getting this sample is a very good surfacing. So you can see this, the surface roughness of this one is 0.09 micrometers, whereas this finish is 0.22 micrometers. So now what we observed is directly going for this abrasive flow finishing or ultrasonic abrasive flow finishing may not be improved that much, but the combination of grinding and finishing improved better. So initially we removed the surface or we finish the surface by grinding process, and then we can go for the finishing process. Then we are getting the very good results. And this is the same 8 samples. This is micro hardness of the different samples. So micro hardness also less for this one, right? So uh, of course, among these 4 samples, if you take this is less, and among these 4 samples, this is the less. So like this, we got different surface hardness. So then, because this UMF easily removes these low hard surface peaks, okay. So we got less surface hardness on this sample, okay, because of the heat treatment, already grain structure changes are there, and slightly heat treatment changes the material properties, fine grains will be there, okay, and because of this one the hardness is slightly reduced, internal stresses will be relieved. So then finishing process reduced the micro hardness of this component. So then if you see surface roughness, this is also same. Of course, that is already mentioned in the microstructure component. So this one is giving a very, sorry, this one is giving a very less value among these 4, and this one is giving very less value among these 4. But if you compare this one and this one, again, this is the best and this is the next best. So the surface roughness also less when we perform the abrasive ultrasonic casted abrasive finishing process on the heat treated and grinded sample, then we are getting the best results. So this is what we observed in the residual stress analysis. So if you see, these are the values in the non-heat treated samples. Okay, so these are the values in the heat treated samples. So if you see, either heat treated or non-heat treated, the residual stress is negative after the ultrasonic assisted abrasive finishing process. That means all these are the tensile residual stresses positive, right? And whereas these two are the compressive residual stresses. Already I told you in the starting itself, this tensile residual stresses observed is due to the high temperature gradients and also rapid cooling in both as-built samples, and also residual stresses after heat treatment are reduced both compared to non-heated samples. These are reduced. However, this is in tensile nature before the finishing process. But this finishing process is giving the compressive residual stresses because the residual stresses got relieved, and these are almost compressive nature, which will be very helpful to improve the life of the component or to get the fatigue life of the component. So that means the lifetime of the component is good. Of course, we took only a rectangular flat components, but the components like any of the complex shapes, the life fatigue life is very important because stress concentration will be there on the peak corners, so that the fatigue life is very important. So this is also wear analysis. So wear resistance also good because already I told you the wear resistance and corrosion resistance are good for the heat treated and grinded and finished surface. So this is because of the better finish. So RA value is less. So obviously wear resistance is more and corrosion resistance is also more. And also the because of the internal residual stresses also, it will be helpful to reduce the wear and to reduce the corrosion. Okay, so of course corrosion values are not given here, but we can able to reduce the wear and corrosion also uh, because of this process. So this is what the analysis of application of ultrasonic assisted magneto-abrasive finishing process on additively manufactured components. The same thing we use on the general component also, but additive manufacturing components, it will be very useful. That is what we applied in the post-processing technique, because this is the one, no one used this technique till now. That's why we used this one. So this is what we perform already, and results are good. But here again, some limitations are there in this process. As I told you, here if you see, the fixer is rectangular and the workpiece is also rectangular shape. But if the workpiece is a complex shape, then how can you finish that one? So because if the workpiece is complex shape, because the brush is touching on the surface like this, okay? So the brush is touching on the surface like this because this is all the brush, right? So which is rotating. So you can see this is the shape of the brush. But if the workpiece shape is like this or something like this, then there is no variation. So it will apply more pressure here, it will apply less pressure here. So this process has a certain limitation, uh, especially in the additive manufacturing components. Of course, we can able to use this process for uh, irregular shapes also. But if you make this brush flexible or shape dependent of the workpiece, then it is more useful. So that is why the next advancement in this process is abrasive flow machining. So if you see, this is the setup. Okay, so this is the fixer, right? And these are the media cylinders. So this one is media cylinder, and this one is also media cylinder. This one media cylinder. So what is this media cylinder is? It's nothing but the media will be there and which will move over the surface, okay, and so that what will happen is the flow, abrasive flow, you can see the word, the same abrasive media will flow over the workpiece. So then we can get the finishing. I will show you more details. So this is the one media. That means instead of mixing the abrasive particles and iron powder, we mix with abrasive media normally with polymer or some other gel type of material, so that it becomes like sticky nature, and it is then here this is the fixture. So inside we have a workpiece, and these are media cylinder 1 and media cylinder 2. So what will happen is the media is flowing downward and upward, and here we have the workpiece, so that what will happen is the media is flowing over the workpiece, right? So because of this movement of the media, the surface of the workpiece is cleaned, or again the finish will be there. So here the setting is the extrusion pressure. That means what is the pressure you are applying here, and the number of cycles, that is how many times you are moving the media, and then flow volume and its speed. So how much amount of media you are sending, and its volume. Again, the media contains how many number of particles, what is the viscosity of this media, etc., etc. So that is the viscosity or rheology of the medium, and abrasive type, size, and concentration of the abrasive particles. So these are the settings we need, we can do in the abrasive medium. And then the workpiece configuration, maybe it is going either lengthwise or area wise, or and also it is the hardness of the workpiece is also important. So these are the elements which are going to influence the material removal rate as well as the finish what we are getting on the workpiece. So this is what I'll show you another example. So for example, you take the cylindrical workpiece. So the media is flowing like this. Okay. So this is what the media flowing. Okay. So this media contains this green is the abrasive particles, right? So I will give you one small example. Nowadays, of course, maybe the ladies know more. So many are using nowadays face wash, right? So if you see the face wash, these type of particles are there, not in all the face washes. Some of the particles are there in the face wash. So these are nothing but acts as a scrub over your face. So the concept of this one is not only giving the foam over your face, and these particles are useful to scrub as used as a scrub. The similar concept here. So this media is flowing. This one is going to uh, strike the workpiece, and also this one is going to uh, just a second. So this is what the principle where the abrasive flow machining is or finishing is used. So this also helps to remove this one. So this one also we can apply to the additive manufacturing techniques. Okay.
Sir, request, sir. 5 more minutes, you're going to
Yeah, sir.
conclude because
So
questions
then
are.
this is what
Today.
actually I'm showing the media. Okay. So these are the different types of media we can use. And this is the movement of the media over the surface of the workpiece. So we can keep the workpiece like this. So this is maybe the internal surfaces we can able to finish with the media flow. And this is the setup where we can, the real setup of the AFM setup. And this is actually morphology of the abrasive medium. So before finishing and after finishing, how the abrasive particles are there, because the material removed from the workpiece is sticking to the abrasive media that we can observe in the SCM images, etc. And this is also the morphology of abrasive media after finishing. So before finishing or after finishing, you can observe that the media is containing some of the workpiece particles or materials. So this is what I already told you, number of cycles, or this is what surface morphology. This is as-built component, and this is the finished component in the AFM process. So this is not from my experimental setup. This is just from the uh, literature only, and this is not additive manufacturing component, normal component. So we can apply this process also to the additively manufacturing component, which is more useful for complexer shapes. So we can study all these things, and this is at surface morphology like this. So we can study all the parameters of this one. And one more thing is, this is the development of ultrasonic assisted abrasive flow machining process. The same thing, whatever we given ultrasonic assisted vibration, this one also we can give. So media flowing like this, at the same time we give vibration in this direction. that is to change the direction of media and to give more complex movement of the abrasive media to get a better finish. So like this. So instead of this movement, the particles are moving randomly and striking to the surface like this. So to improve this, maybe you can use ultrasonic vibration assisted machining. So this is another advanced approach. So we can give ultrasonic this movement and ultrasonic vibration as well as rotation also, like this, rotating and going. So if you give these three types of movements, then maybe you can get more better accuracy and more better finish in the process, right? So this one still in the development stage, and but the initial two process already developed and tested on the additively manufacturing components. So that's what maybe we can use MAF or UA, MAF or AMF or UA, MF or this one or UA, FM. So whatever. These two already we tested. This one in the development stage for the additively manufactured components. Maybe if anyone interested, you can try this one also, right? So this is what the post processing of the additively manufactured components by this process. So thank you very much. If you have any questions, please ask me.
Participants, any queries, please ask sir. Virtually raise your hand. Otherwise, you unmute your mic.
Participants, you can raise a question. You can unmute your mic and you can raise a question.
Okay, sir. Thank you. Thank you, sir. You have given a nice lecture.
Thank you, sir. Thank you very much.
Okay. Thank you, sir. Sir, now all the participants can give switch on the audio video. So, including speaker, sir, please. Including speaker also.
So we shall have a photo session now, please.
Thank you, sir. Vignesh, Akash. Sir, please switch on your video, sir. Please. Murugan Chandrakumar. So, very money. Sangeet Kumar. Jagan.
Some chat.
Please switch on video, sir. Dear participants, please switch on video.
Okay, sir. Can I leave the meeting?
Thank you, sir. Thank
Yes,
you.
sir. Thank you very much, sir.
Okay, sir. Thank you.